Okay, so welcome to the first lecture of week 7. And last week in the analysis part, we completed chapter 1, which was on real numbers, in particular the least upper bound property of R. And today we'll start with chapter 2, and this week and the next one will basically be about this chapter. And this chapter is on sequences and their convergence. So the first task is to understand what a sequence is. Now in everyday language, we use the word sequence. For example, we say a fortunate sequence of events, by which we mean that there was a first event which led to a second event, a third event, and so on. And so we can identify a list of events in which there's a first event, a second event, a third event, and so on. In the same way, a real sequence is an infinite list of real numbers in which there is a first term of the sequence, a second term or member of the sequence, the third term, fourth term, and so on. So in other words, a sequence can be thought of as a function from the set of natural numbers 1, 2, 3, and so on to the set of real numbers. So 1 is mapped to the first member of the sequence, A1, 2 is mapped to the second term of the sequence, A2, 3 is mapped to the third term, and so on. So a formal definition is that a sequence is just a function from n to r. And indeed, to specify a function from n to r, we need to specify what is f1, f2, f3, and so on. And we think of these as the members of the terms of a sequence. This is the first member of the list, the second member of the list, the third member of the list, and so on. So just the notation is a little bit different in that we list these values sequentially as a1, a2, a3, and so on, these real numbers, with the understanding that then f maps 1 to a1, 2 to a2, 3 to a3, and so on. And mostly we will use this notation for this sequence, namely a with the subscript n, and then n is referred to as the index of the nth term. So an is thought of as the nth term, and n, the subscript, is then thought of as the index. Okay, and these indices run through the natural numbers. Okay, so what do we want to do with sequences in calculus? Well, we want to discuss their limiting behavior, and that will be the main concept, what is meant by a sequence being convergent with a certain limit. But before we get to that, let's see some examples of sequences. So the first example I have is where the nth term is just given by the reciprocal of n, 1 by n, for n in n. So the sequence we can succinctly write as 1 by n, where the n runs over the natural numbers, and so the nth term is 1 by n. So the first term is 1 by 1, which is 1, the second term is 1 by 2, the third term is 1 by 3, and so on. And since the sequence is really a function, we can draw its graph. Okay, so if we on the x-axis have the natural numbers 1, 2, 3, and so on, then the point on the graph of this function will be of the form n comma an, okay, where an is the nth term of the sequence. And so in this case, the terms of the sequence look like this. The first term is 1, the second term is half, the third term is a third, and so on. And we sort of see that, the terms of the sequence seem to be settling down to 0. Okay? So the distance to 0 is becoming progressively smaller. Now, a sequence may also be specified recursively, in which we specify the first term or the first few terms and give a rule of how, given a certain bunch of terms, you can calculate the next term in that sequence using these preceding terms. For this particular sequence also, we can write this sequence or define the sequence recursively, with a1 being specified as 1, and then here is the rule for determining the n plus first term given the nth term. It is given by an plus 1 is n divided by n plus 1 an for n in the natural number. So if you look at what this rule delivers, you get a1 is of course 1, and then a2, which is a1 plus 1, that can be determined from a1. a2 will be 1 divided by 1 plus 1 a1, so that's a half times 1, which is half, and then a3 can be determined from the a2, so 3 is equal to 2 plus 1, so a3 will be 2 divided by 2 plus 1 a2, which is a2 is half, so You see these two cancels and you get a third and so on. So in this way, one can check that you get the same sequence as before. So sequence can be specified by telling you what the nth term looks like in terms of n, or there can be a recursive definition as we have seen. Here is one more example of a sequence where the nth term is given by minus 1 to the power n. So the terms of the sequence, if n is odd, is always minus 1, and if n is even, it's always plus 1. So the terms alternate, minus 1 plus 1, minus 1 plus 1, and so on. And the sort of pictorial representation of the sequence in terms of its graph then looks like this. It starts at minus 1, 1, minus 1, 1, and it sort of keeps toggling between these two values. Here is one more example. If I look at the sequence whose nth term is given by n, so then the terms of the sequence are just the usual natural numbers 1, 2, 3, and so on. So now the sequence is actually the identity map where n is sent to n itself. And the graph of this sequence looks like this. So we see that the terms don't stay bounded, okay, but they sort of increase without bound. Here is one more example of a sequence where the nth term is this sort of partial sum where you add up the reciprocals up till n. So 1 plus half plus a third and all the way up till 1 by n. So the first term is 1, the second term is 1 plus half, the third term is 1 plus half plus a third, and so on. So we see that each time we are adding something positive, so the terms are increasing, but it's we are adding ever so small quantities as you proceed in the sequence. For example, at the millionth step, you would be adding 1 by a million. So there's a very tiny incremental change. So it's not clear if the terms of the sequence stay bounded or not, because maybe these increments add up and maybe the sequence is not bounded, who knows. Right now, we don't know that, but at least the terms are increasing. We see that. And here I've plotted the graph of this function, which sends n to this number. So we have seen several examples of sequences, but what do we want to do with sequences? As we mentioned earlier, in calculus and analysis, we are interested in the limiting behavior of sequences. In other words, what the sequence looks like for large n. And the typical questions are whether the terms of the sequence stay bounded. Is there some big upper bound and a big lower bound so that all the terms lie below this big upper bound and above this lower bound? Or is it even the case that the terms sort of settle down around a value, and sort of the farther out you go in the sequence, the closer you are to this value L, which is then thought of as the limit, and then we talk of a convergent sequence with limit L. So these are right now just intuitive notions that I'm talking about, that you want to decide whether or not a sequence is convergent with a limit L. We have not yet defined this notion, but that's another useful concept that we want to have to define properly to use in analysis. For example, things like this you have already met in calculus. For example, when we actually talk of the area under the graph, you might have learned that, well, what we are actually doing is we are approximating this area by exhausting it with rectangular areas. So if we divide it into n parts, then this is the base width, and then we multiply it by the value of the function at one of the endpoints, say this one, so that you get these lower triangles, and then you add them all up. So that's the sum of these rectangles, and then this you should think of as the nth term of a sequence. And what we are interested in is what this looks like for large n. Okay, what value does it sort of tend to or sort of settle down to, and that is what we think of as the area. So we see that in integration this notion arises, and also if the function is differentiable everywhere, and if we want to calculate the derivative at a point, we take the limit of difference quotients. And if you take a sequence of values here, say I look at the difference quotient for c perturbed by 1 by n, so I look at f c plus 1 by n minus f of c divided by 1 by n, and then I might want to look at the sequence whose nth term is this, and want what is the limiting behavior of this. Assuming that the function is differentiable, then this would be the derivative at c. So this is just some vague motivation, But actually sequences play a very important role in all of analysis, in Fourier analysis, Fourier series, and in power series and so on. So it's quite an important concept. Besides just this calculus motivation, in analysis, sequences and their limiting behavior play an important role. So what we want to do in this chapter is first of all understand what it means to say that a sequence is convergent with a certain limit, and then deduce ways of finding out if a sequence is convergent or not without having to go through the definition, okay, because that will show a much more richer structure to this notion. Okay, so the first task is, how do we define what is meant by a sequence being convergent with a certain limit? Now, if we look at our earlier sequence 1 by n, it seems that the values are settling down to 0, and the terms of the sequence do seem to get closer and closer to this 0. So a naive first guess would be, why not say that, well, the distance to this number, which we call the limit, should sort of monotonically decrease, and the distance to this limit becomes smaller and smaller. Sort of more mathematically, whenever you take an index which is larger than some other index, then the distance of that larger index term to the limit, in this case, in the case of this sequence, we guess it to be 0, is less than the distance of the previous or the earlier terms to 0. And indeed, in this case, it seems to work out, because when capital N is bigger than this little n, then this quantity is just 1 by capital N, and that is certainly less than 1 by little n, which is this quantity. However, that's not a good definition, because, for example, if I look at this sequence in which I add 1 to each term, so that I have the sequence 1 plus 1 by n, the nth term is given by this whole sequence is lifted up by a distance of 1. So now, if this sequence were convergent to 0, I mean, we visibly see that this sequence is convergent to 1. Whereas this earlier guess of a definition is not good, right? Because again, the distances are decreasing. I mean, to 0, they are still decreasing, you see. But it's not the case that this sequence is convergent to 0. In fact, it should be convergent to 1. But then you might say, well, the terms of the sequence are not getting arbitrarily close to 0. Okay, all right, I accept that criticism. But then, how do we actually define what is meant by a sequence being convergent? And also, we want to allow the terms of the sequence to oscillate around a certain value and then settle down gradually while oscillating to this limit. So just saying sort of some very simplistic definition that the terms are getting closer and closer is not good, because it may be the case that we want to say that the sequence is convergent, but the distance to that limit may, oscillate. It might increase a little bit, then it might decrease, and then it increase and decrease and so on. So here is an example. Suppose I look at the sequence an, where the nth term is given by 1 by n if n happens to be odd, and 0 if n happens to be even. So then the terms of the sequence look like this. At all the even places it's 0, but at the odd places it sort of goes as 1 by n. So you have 1, then 0, then 1 by 3, then 0, 1 by 5, and so on. And you see that the terms of the sequence do seem to sort of settle down to 0, but you see that the distance to 0 has this odd behavior. The first the distance decreases, then it increases, then it decreases, then it increases, and so on. Okay, so somehow our definition of the convergence of a sequence to a certain limit should be robust enough, or should be wide enough to also capture this thing. So we should not just rely on this simplistic closer and closer stuff, because we want to also capture these kind of situations. So let's sort of pause and think, what do we actually mean when we sort of intuitively think that the terms of the sequence are settling down to a value? What we actually want is that no matter what distance we think of, say 0.00001, then if I look at that limit number, and if I look at sort of a strip of width, this small distance, then if I go far enough in the sequence, then all the terms lie in this strip. okay, so that their distance to this limit is smaller than this 0.0001. And moreover, this should happen with every distance, that positive distance you specify. For example, if I instead of 1 divided by million, if I take 1 divided by billion, indeed there should be some large enough index such that beyond that all the terms lie within this strip of 1 divided by billion from the limit. Okay, so that's what we actually want, and what the sequence does while settling down we don't care about. Okay, so that's what we actually mean by sort of settling down to this value. All right, so let's sort of try to put this intuitive feeling in sort of mathematical words. So here is the definition, and we will revisit this after looking at the definition and sort of carefully analyze, is this really what does the job. So the definition is that a sequence an is said to be convergent with limit L, so this is L is some real number, if no matter what distance epsilon you specify to me, so for every epsilon positive, there exists an index n. Okay, so beyond which we are guaranteed that the distance is small. So there exists some sort of milestone along that sequence, as that beyond that, such that for all the terms beyond that index, so for all the indices little n which are bigger than this milestone index, you have that the distance of the nth term to L is smaller than epsilon. So recall that the distance between an and L is given by the absolute value of the difference between the two real numbers that we saw last time, right? So let's read this again now using just the mathematics. So sequence is said to be convergent with limit L if for every epsilon positive there exists an capital N such that for every little n bigger than n you have that the distance of an to L is smaller than epsilon. And sort of in intuitive words, this says that for any distance epsilon positive you specify, there exists an index such that if you go far enough in the sequence, that is beyond this index n, the distance of an to L is smaller than epsilon. Indeed, this is what we meant, and let's see this once again pictorially. So the sequence is said to be convergent with limit L if there exists this L. There should exist first of all this limit L, which is a real number. Okay, so I mark that off here, and this is where the graph of the sequence will live. So here you have on the x-axis the natural numbers. So first of all there should exist this L, a real number, such that whatever epsilon positive we pick, so that specifies the distance level. Say maybe it's 1 divided by a million, and we look at this shaded strip. Why this shaded strip? Because the saying that mod an minus L is less than epsilon is the same as saying that an is less than L plus epsilon and bigger than an minus epsilon. So all the real numbers whose distance to L is less than epsilon lie in this open interval on this vertical line, you see, because all the real numbers x such that mod of x minus L is less than epsilon is the same as those x's which lie in the open interval L minus epsilon to L plus epsilon. So they lie over here. Okay. Alright, so no matter what distance level you specify, and we consider the shaded strip of width epsilon around the horizontal line passing through L, there exists an index n. So this is that milestone index, such that all the terms with indices little n bigger than capital N lie in this strip. So in other words, if you look at capital N plus 1, capital N plus 2, capital N plus 3 and so on, and look at the corresponding terms, then those corresponding terms satisfy this. And what does this mean? That means that an is less than L plus epsilon, so it lies below this horizontal line, and is bigger than L minus epsilon. In other words, it lies above this horizontal line. So in other words, it lies in this strip. Okay, so saying that mod an minus L is less than epsilon is the same as saying that these blue dots lie in this strip, in the shaded strip. Okay, and this should work with every distance you challenge me with. So for example, if instead of 1 divided by a million, if I take 1 divided by a billion, then again there is some index. There again exists a corresponding milestone index, maybe much bigger. So maybe here n equal to 3000 worked, maybe here you need 30,000 or 9,000 or something like that, such that beyond that all the terms lie in this now narrower strip corresponding to 1 divided by a billion. Okay, so given any epsilon, of course this capital N then depends on the epsilon. Okay, so if for epsilon equal to 1 by a million, maybe 30,000 works, but if I take epsilon equal to 1 divided by a billion, then maybe we have to take 90,000, and if epsilon is equal to 1 by a trillion, maybe you have to take 9 billion as the n, and so on. Okay, so that's the definition. It's quite a mouthful, but we will get used to it. And the thing is, to show that a sequence is convergent with this limit, what we actually have to check is that for every epsilon positive, we have to produce a capital N, which depends presumably on the epsilon, such that, and then we have to check this, that for every little n bigger than this index, you have that the distance of the nth term to L is smaller than epsilon. Okay, so let's see some examples of checking this. And before we do that, let me just mention that, okay, so let's recall again the definition. So an is convergent with limit L if for every epsilon positive there exists an index capital N such that beyond that index the distance of the nth term to the limit, the claimed limit, is less than epsilon. And if this happens, then we sort of succinctly write it as limit as n tends to infinity an is equal to L. So this is read as limit as n tends to infinity an is equal to L, and by that we mean that the sequence an is convergent with limit L. And if there does not exist a real number L such that this happens, so that the sequence is not convergent to any L, any real number L, then we say that the sequence is divergent. Okay, so let's see some examples of convergent and divergent sequences. So let's take the sort of example that we started with, namely 1 by n, where the nth term is given by 1 by n. I claim that this is convergent with limit 0. Sort of we had seen that intuitively, but now let's use the definition to check this. So what do we have to check to prove this claim that the limit as n tends to infinity 1 by n is equal to 0? We have to check this sentence over here, that for every epsilon positive, there exists a capital N such that beyond that n, the distance of an to L is less than epsilon. So this should work with any epsilon you give me. So always with some analysis proofs like this, you start with some rough work and develop a strategy of picking this capital N and then seeing that it works, and then you write down the proof carefully. Okay, so we start with rough work. So let epsilon positive be given. So what do we want? We want a capital N such that for every little n bigger than capital N, mod of an minus L is less than epsilon. Now, what is an minus L in this case? L we are claiming is 0. We have guessed that the limit is 0. And an is 1 by n. So what we want is, given this epsilon, I want a capital N such that beyond this n, you have that mod of 1 by n minus 0 is less than epsilon. But this is a positive number. You have 1 by n. Mod of that is 1 by n. So what we want is 1 by n is less than epsilon. In other words, n epsilon should be bigger than 1. So the question is, given an epsilon, how do I choose a capital N such that for every little n bigger than n, n epsilon is bigger than 1? Now, of course, if I, with a capital N over here, if I already choose the capital N so that capital N times epsilon is bigger than 1, then certainly for little n bigger than capital N, you will have little n epsilon will also be bigger than 1. And having a capital N epsilon bigger than 1 is indeed possible by the Archamidian principle. Indeed, the Archamidian principle says that if I take this as my y is 1, and x as epsilon, which is positive, then there exists a natural number n such that n, capital N times epsilon, is bigger than 1. Okay, so given the positive epsilon, I choose my capital N in this way, such that capital N times epsilon is bigger than 1, which is guaranteed by the Archimedean principle. Once I do that, let's quickly check that it does the job. So for little n bigger than capital N, then I have that 1 by little n is less than 1 by capital N. And thanks to this, 1 by capital N is less than epsilon. And so I've got that 1 by n is less than epsilon as I wanted. So right now we are still at the rough work stage where we have the strategy that given an epsilon, I know a method of producing this capital N such that it does the job, that this sentence is satisfied. So now we write down the proof, okay, properly. So let epsilon positive be given, then here is the step of choosing the capital N. Choose the capital N such that it satisfies capital N times epsilon is bigger than 1. And we are guaranteed that there exists such a capital N because of the Archamidian principle. Once I choose this capital N, you see it depends on epsilon. Then for every little n bigger than this capital N, we have to check that this happens. Mod of an minus L is less than epsilon. So let's find out. Mod of an minus L is equal to mod of an is 1 by n and L is equal to 0. And since this is positive, this is 1 by n. But since little n is bigger than capital N, this is less than 1 by capital N. And 1 by capital N is less than epsilon because of this thing, right? And so what have we checked? We have checked that given any epsilon positive, that's this highlighted bit, there exists a capital N which is chosen in this way so that it satisfies n, capital N times epsilon is bigger than 1. We have that for every little n bigger than capital N, you have that the distance of the nth term to L is less than epsilon. So this highlighted yellow portion is exactly this statement which we have verified. And so we have checked that this sequence is convergent with limit 0. In other words, we can write it succinctly like this. So the first time you see this, it looks quite complicated. But this was a very simple sequence, and we'll get used to this kind of reasoning where you have to do some rough work first and then you have to write down it more carefully. And also, it's not the case that we are going to sort of torture ourselves with, very complicated examples where you have, you have to choose some very complicated capital N or exotic capital N corresponding to an epsilon. No, we are soon going to learn ways of deducing convergence of sequence without having to go through the definition. Okay, so we will see that if a sequence has this and this property, automatically it is convergent. And if you break down a sequence into simpler sequences which are convergent, then you can deduce the limit also. Okay, so we'll learn all these things. But let's see, first of all, some more examples, and I'll take one more very simple example just to sort of get intuition about this definition in simple cases first. So let's consider the constant sequence. So suppose C is a real number and you take the sequence whose nth term for all n is given by C. So this sequence is just C, 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 and so on. So for example, if C equal to 1, it's the constant sequence 1, 1, 1, 1, 1, and so on. If C equal to minus root 2, then this is the constant sequence minus root 2, minus root 2, minus root 2, minus root 2, and so on. So of course, if I look at the graph of this sequence, well, it doesn't budge at all from this value of C. So of course, the limit has got to be C if there's any sort of justice in this world. So let's prove this using the definition. Okay, so what do we have to check? Well, given any epsilon positive, we want an index capital N such that beyond that index, the distance of the nth term to L is less than epsilon. Well, what's the nth term? That's C for all n's. And what's the limit we are guessing? Well, it's also the real number C. So what's mod of C minus C? That's mod 0, which is 0, and that's certainly less than epsilon because epsilon is positive. So this is true irrespective of what little n you take. So it seems that any capital N you take seems to work, right? And of course that makes sense because what did we want? We wanted, given any positive epsilon, for all the terms to lie within the strip of width epsilon around this C. But all the terms are already at C, so you don't have to do anything. You can take capital N to be any milestone index you want, right? So beyond that, we are guaranteed that the terms in fact have distance 0 to this limit. So let's make the proof complete. So this was again some rough work. So given the positive epsilon, take any capital N, your favorite capital N. Let's take capital N equal to 1, doesn't matter. Then for every little n bigger than this capital N, we have that mod of an minus L, the distance of an to L, is equal to mod of C minus C, because an is C and L is C, and this is mod 0, which is equal to 0, which is less than epsilon. And so, given any positive epsilon, we have produced a capital N, such that for every little n bigger than capital N, you have that the distance of an to L is less than epsilon. So we have checked that sentence that we wanted to, and so this constant sequence is convergent with limit C. Okay, so we have seen two examples of convergent sequences. Let's see an example of a divergent sequence. So this is the sequence that we had met before, sort of the alternating sequence, which takes values -1, +1, -1, +1, alternatively depending on whether n is even or odd. For all the odd things, it's always -1. For all the even things, it's always +1. Now, of course, we know that the sequence sort of keeps hopping between these two numbers and it never really settles down to anything at all, right? And so we intuitively know that this sequence is not convergent, but let's prove this using the definition. So let's suppose that L is a real number such that the limit as n tends to infinity of -1 to the power n is equal to L. So in other words, we are supposing that the sequence is convergent with limit L. Now this L has got to be somewhere, but wherever it is, you see that the distance to either the even terms or the odd terms is going to be bigger than 1. If it is bigger than or equal to 0, you see that the distance here is bigger than 1, and if it is L is less than 0, then the distance to the sort of even terms is going to be bigger than 1. So that's going to be the source of the contradiction. So if we suppose that the sequence is convergent with limit L, then what we know is that for every epsilon positive there exists a capital N, such that for all the indices beyond this capital N, you have that the distance of the nth term to L is smaller than epsilon. Now you see that one of the two distances is going to be too large. So let's see what happens when n is even. So if I take a little n, which is bigger than capital N but even, so for example 2 times capital N, then this is equal to +1. So you have that mod of 1 minus L is less than epsilon. What does that mean? That means that the distance between 1 and L is less than epsilon. In other words, L lies within a distance of epsilon from 1. So it lies in this yellow open region, right? Now for n odd, for example, and bigger than this capital N, so for example, if I take 2 times capital N plus 1, then this is equal to -1, and so you have that the mod of -1 minus L is less than epsilon. In other words, the distance between -1 and L is less than epsilon. So if I look at this width epsilon around -1, then L has to lie over here. But you see, if the epsilon is smaller than 1, then there is no overlap between these regions. You see that they will start overlapping only when epsilon is equal to 1 or bigger. So if this was true for every epsilon positive, so if I choose epsilon less than 1, then we are going to get a contradiction, because L is supposed to lie in this open, in this yellow region as well as this open region, but they don't overlap at all, right? So that's going to be our contradiction, right? And let's carry it out. So we want an epsilon less than 1. This sentence was true for all epsilon positive. So in particular with epsilon equal to half. Half is strictly less than 1, so that's why we take that. So that's a positive number. And since the sequence is assumed to be convergent with limit L, we know that there exists an index capital N such that beyond that index, the distance of the nth term, which is -1 to the power n, to the limit, which is L, is less than this epsilon, which is half. And if I take the n's to be even, so for example 2 capital N, which is bigger than capital N, then you have that this inequality becomes mod of 1 minus L is less than half. So let me label this inequality with a star. And if I take this little n, which is bigger than capital N but odd, so for example 2 times capital N plus 1, then this inequality, since this is now minus 1, becomes minus 1 minus L, that's less than epsilon, which is half. Okay, but let's simplify this a little bit. You see, if I take minus as a common factor, I'm left with 1 plus L, and the mod of AB is mod A times mod B, so this is mod of minus 1, which is 1, times the mod of this thing, so that's mod of 1 plus L. So we have got that mod of 1 plus L is less than half, because this was less than half. So let me label this inequality with a star star. So from these two inequalities, what do we get? If I add these two, half plus half, I get 1, but that is bigger than 1 minus L from this inequality and 1 plus L from this inequality. And by the triangle inequality, remember that we had proved that last time, this is bigger than or equal to the sum of these two, because the mod of A plus B is less than or equal to mod A plus mod B. Right? So because of that, triangle inequality, this is less than or equal to the sum of the mods. Now you see, this minus L and plus L cancel, and I'm left with 2. So what I've got is 1 is strictly bigger than 2, which is of course a contradiction. So assuming that there is a limit for this sequence, we have arrived at a contradiction, so there is no such real number such that this sequence converges with that limit. So this sequence is divergent. Okay. Of course, there are many simpler ways of showing that this sequence is divergent too, and as we go along, we'll see these other theorems, the use of these other theorems to show that this is divergent. But this was using sort of the definition. Okay, so now I want to show this theorem which says that the limit of a convergent sequence is unique. So if you know that a sequence is convergent, then it can have only one limit. It cannot be the case that it converges to this as well as some other number. And that's sort of intuitively clear, because what do we mean by the limit? That the terms of the sequence are settling down to that value. So it cannot sort of settle down to two things, right? So to sort of make it a bit more precise, suppose that a sequence AN is convergent with two limits, L1 and L2, with L1 not equal to L2. Well, if L1 is not equal to L2, there is some distance between them, right? So if we take a strip of width which is less than half the distance and consider two strips, one about L1 and one about L2, okay, with this width which is less than half the distance between the two, then these two strips don't overlap as shown in this figure, you see. Then if the sequence is convergent with both of these limits, that means that, well, there is some index beyond which all the terms lie in this shaded strip, and there is a certain index such that all the terms lie in this shaded strip, but they cannot lie in both shaded strips at the same time. They are all supposed to lie in each of these shaded strips, but they don't overlap, and so that's the contradiction. Okay, so this is sort of the intuitive argument, but let's now make it more precise. So we are assuming that the sequence is convergent with two limits L1 and L2, with L1 not equal to L2. Now since L1 is not equal to L2, this is a non-zero number, so the mod of that is going to be a positive number, and that divided by 2 is also a positive number. So let's take this as our epsilon. That's a legitimate positive number. Since the sequence is convergent with limit L1, there exists an index, let's call it N1, such that beyond that index, the distance of all these terms AN to L1 is less than epsilon. And since we are also assuming that the sequence is convergent with limit L2, for this positive epsilon, there exists a milestone index N2, such that beyond that index, all the terms of the sequence are also supposed to satisfy this. Mod AN minus L2 is less than epsilon. So now if I take an N which satisfies both, that it's bigger than N1 and bigger than N2, for example, N equal to N1 plus N2, then both of these things are satisfied, then both of these inequalities should be satisfied, because whenever little n is bigger than N1, this is supposed to be satisfied, and now I'm indeed taking something bigger than N1, and likewise for N2. So if both of these are satisfied, let's look at what 2 epsilon is. Well, 2 epsilon is mod L1 minus L2, and I know something about AN minus L1 and AN minus L2, but I don't yet see an AN there. So let me artificially produce that by adding and subtracting AN. Okay, so this is just 0, so I have not produced any change. And now I use the triangle inequality. This is less than or equal to mod of L1 minus AN plus mod of AN minus L2. Okay. Now this mod of any number is the same as the mod of minus of that number, because minus of that number is just minus 1 times that number, and mod of minus, let's call that number x, mod of minus x will be mod of minus 1 times mod x. Mod of minus 1 is 1, and so mod minus x is the same as mod x. So the mod of this one is the same as the mod of minus of that. Minus of that is an minus L1. So this mod of L1 minus an is the same as mod an minus L1, which we know is less than epsilon because n is bigger than n1. Similarly, mod an minus L2 we already know is less than epsilon because n is bigger than capital N2. So this is less than epsilon plus epsilon, which is 2 epsilon. So what we have got is 2 epsilon is strictly less than 2 epsilon. But that can't happen in light of the trichotomy law, right? Because 2 epsilon is equal to 2 epsilon. So this is wrong. And all this happened because we assumed at the outset that the sequence is convergent with 2 limits. So that cannot be true. And so the limit of a convergent sequence is unique. And in fact, that justifies why we can use this notation, because once you know the terms of the convergent sequence, then unambiguously we know what the limit is. So it makes sense to write for this limit this notation just in terms of the sequence. And sometimes, as I mentioned earlier, we read this as saying that the sequence an converges to L as n tends to infinity. Okay, so we will use both of these phrases. Either the sequence is convergent with limit L, or that we can also equivalently say that an tends to L or converges to L as n tends to infinity. Okay, so what we have learned is what is the definition of the notion of convergence of a sequence with a certain real number as the limit. And we have seen some examples where we checked that the sequence is either convergent or divergent using the definition, but we noticed that using the definition is cumbersome. So what we are going to do in the rest of the chapter is sort of discover ways to avoid this hard work or toil. But of course there's a more important aim also, namely that sequences may not be explicit, but you may know some properties of it, and then we nevertheless want to deduce that the sequence is convergent, because then this kind of a thing is, for example, used in existence theorems in analysis and so on. So we need to learn about these things, these results, which tell you when a sequence is convergent without actually checking by brute force that the definition is satisfied. So the kind of theorems that we learn is that if the sequence has such and such a property, automatically it's convergent. Or if the sequence is broken down into these elementary sequences which are convergent with known limits, then how to determine the limit, okay? Things like that. So one example of such a theorem, which we will soon show, is that if a sequence has the properties that it's bounded and that it's monotone, then it's convergent. So right now we don't know what bounded means and what monotone means. Bounded roughly means that the terms of the sequence don't grow without bound. They sort of can be bounded by some top value and some value below. So all the terms of the sequence lie in some strip. That's roughly speaking what bounded means. And monotone just means that the terms of the sequence are either increasing always or they are always decreasing. So that's a theorem that we'll soon learn. But towards that goal, we will now start learning about what bounded means precisely and what monotone means precisely, and then we'll prove this theorem. Okay. So let's first explain what's meant by a bounded sequence. So a sequence an is said to be bounded if there exists a sort of bound capital M, which is a positive number, such that for all the terms of the sequence, their absolute value is less than or equal to M. Now, this inequality, that mod an is less than or equal to M, is the same as saying that an is less than or equal to capital M and an is bigger than or equal to minus M. So This inequality is equivalent to saying that an is less than or equal to m, and an is bigger than or equal to minus m. So in other words, all the terms lie below this line at level m and above this line which is at level minus m. So all the terms of the sequence lie in this strip. Okay, so the sequence is bounded, and let's show some equivalent statements. So here is a theorem, a sort of useful theorem, which says that bounded means one and the same as any of the following sentences. So let an be a sequence, then the following are equivalent. To say that the sequence is bounded, of course, from the definition, is the same as saying that there exists a bound capital M which is positive, such that for every index, the mod of the nth term is less than or equal to m. And that's the same as saying that this set of real numbers, mod an, where n ranges over all the natural numbers, is bounded. And that's the same as saying the set where we take just the terms of the sequence, that set is bounded. And that's the same as saying, we know that this set bounded means that there is an upper bound and a lower bound, and each of these sentences is the same as any of the others, means the same thing. So to prove this equivalence, we'll simply show that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and 5 implies 1. So then if you challenge me, have we really shown that all the equivalences are valid? That is 1 equivalent to 2, is 2 equivalent to 3, is 3 equivalent to 4, and so on. So of course one-way implications are clear, but for example you might challenge me, how does 4 imply 2? How does 4 imply 2? Well, 2 implies 4 is clear, right? Because 2 implies 3 and 3 implies 4. So 2 implies 4. And how does 4 imply 2? Well, 4 implies 5, 5 implies 1, and 1 implies 2. So 4 implies 2, because 4 implies 5 implies 1 implies 2, right? So if we show that loop of implications, then we have shown the equivalence of any two sentences in this list. Now 1 implies 2 is obvious, because if an is bounded, that is the definition, that there exists a bound capital M such that for all the terms have absolute value which is less than or equal to m. How about 2 implies 3? That's also true, because m is clearly an upper bound and a lower bound is clearly 0, right? Because the absolute value of anything is always bigger than or equal to 0. So there's a lower bound, namely 0, and there's an upper bound, and that's why this set is bounded. How about 3 implies 4? So we want to show that whenever this set is bounded, also this set is bounded. Now, what does it mean to say that this set is bounded? That means that it has an upper bound and it has a lower bound. Actually, we'll just use the upper bound, right? An, we know, is surely less than or equal to mod an, and that's less than or equal to u. So u is already an upper bound for this set, because all the ans are less than or equal to u. And an is also bigger than or equal to minus mod an. Why is that so? Because this is the same as saying that minus an is less than or equal to mod an, right? That we had seen. So, and moreover, minus mod an is bigger than or equal to minus u because of this inequality. So what we have got is that an is less than or equal to u and bigger than or equal to minus u. So minus u serves as a lower bound, and so this set is bounded. So now let's show that 4 implies 5. Well, that's again the definition of what a bounded set is. Okay, so 4 implies 5 is just the definition. And now let's prove that 5 implies 1. So what we have is that there exists u and l, real numbers, such that for every little n, an is less than or equal to u and bigger than or equal to l, and we want to produce a capital M positive such that mod of an is less than or equal to m for all n, because that's what it means to say that the sequence is bounded. So how do you produce this n? Well, we know that an is less than or equal to u. Yeah, an is less than or equal to u. That was the hypothesis. And u is less than or equal to mod u. Mod u is furthermore less than or equal to the larger of mod u and mod l. And that is furthermore less than or equal to the same thing plus 1. I add plus 1 because, by chance this is 0, I would still have m positive. Okay, so I take m as the maximum of these plus 1, and that's a positive number. And what we know is an is certainly less than this quantity, which is what we are taking as m. Similarly, minus an, because of this thing, you see that L is less than or equal to an. So that can be rearranged to say minus an is less than or equal to minus L. Minus L is less than or equal to mod L, which is again less than or equal to the maximum of mod U and mod L. And then I add plus 1 to it, the inequality is still preserved, and that's your M. So what I've got is An is always less than this capital M, and minus An is also less than this M. But mod An is either this or this, and in both cases we have something less than M. And so we have shown that mod An is less than or equal to this M for all n, and so we have shown that this An is bounded. So this can be useful sometimes. So let's see some examples of bounded sequences. So if I look at the constant sequence, of course it's bounded because mod C is less than or equal to mod C plus 1. I add 1 because then by chance if C is 0, then I wanted M to be positive, so I take mod C plus 1, that's a positive number, and all the terms are bounded above by this mod C plus 1, so it's bounded. What about this alternating sequence? Of course it's bounded also, because mod of this is always 1, and that you can take as your M. So it's in fact equal to M, and in particular less than or equal to. The sequence whose nth term is 1 by n is also bounded because mod of 1 by n is 1 by n, which is less than or equal to 1 because n is a natural number, right? So its reciprocal is less than or equal to 1, which we can take as our positive M. On the other hand, the sequence whose nth term is n, the natural numbers, you see, they keep increasing without bound. So we suspect that this is not bounded, and indeed the Archimedean principle will tell us that it's not. Because if we had a bound capital M, okay, M positive, then the Archimedean principle says that there exists a natural number n such that n times 1, which is taken as x, is bigger than this y, which is m. Okay, and so we have got n is bigger than m. So there will be some term which goes beyond this claimed upper bound, and so this cannot be a bound for the sequence. So this sequence is also not bounded. Let's look at this sequence whose nth term is given by this partial sum, 1 plus 1 by 2 square plus 1 by 3 cube plus all the way up till 1 by n to the power n. I claim that this sequence is a bounded sequence. Now how would you go about showing this? So over here we sort of use a trick, but as we gain more experience with analysis, these kind of sort of tricks seem more and more natural. Okay, the trick that I'm going to use is I'm going to replace this complicated thing by a geometric progression sum. The geometric progression sum has the advantage that there's a formula for the sum, and so we get a handle on how big this can get. And if the geometric progression common ratio is strictly less than 1, then we know that the terms are not growing too fast, right? And so there is hope that then you can use that to show that the sequence is bounded. Okay, so let's first see the proof, and then we will again think about what we have done. So what I do is I overestimate 1 by 3 cube by 1 by 2 cube, because 3 is bigger than 2, the reciprocal will be smaller, and when you cube it will still be smaller. And similarly I do that the same thing with each of the remainder terms. So for example, 1 by n to the power n is also less than 1 by 2 to the power n, and for each of the intermediate terms I overestimate it by 1 by 2 to the power in question. Okay, so for example 1 by 4 to the power 4 is less than 1 by 2 to the power 4, and so on. But now you see that we have got a geometric progression over here, and if I take 1 by 2 square as a common factor, I'm left with 1 plus half plus all the way up till 1 by 2 to the power n minus 2, and we know what the sum over here is. The first term is 1, and how many terms are there? Well, it starts at 2 to the power 0 and goes all the way up till n minus 2. So there are n minus 1 terms. So it's 1 minus the common ratio, which is half over here, to the power n minus 1 divided by 1 minus the common ratio. Now you see that this 2 square cancels with the half in the denominator, leaving a half. And you see this 1 minus a positive number, you can overestimate it by 1 minus 0. Okay, so this is bounded above by 1 plus a half, and that is equal to 3 by 2. So what I've shown is that this, with this as m, the nth term of the sequence, the mod of that, because it's positive, is itself, is less than this bound 3 by 2. Okay, so it might seem a little bit out of the blue. Why did we think of the geometric by overestimating it by this geometric progression terms? And that's because we know something about this sum. And luckily, since the common ratio was less than 1, a bound, producing a bound was possible.